So this time we're moving on to section 1.3 of our textbook, and it deals with the concept of the limit. Now, essentially the limit concept is what separates algebra from calculus. The two main ideas in calculus, the derivative and the integral, are based upon the limit process. So we need to understand limits. We're going to understand them first, and then we'll see how they show up as opposed to putting them down the other way. The limit concept, of course, has been around for thousands of years. I mean, one simple thing is to think about a circle and approximating a circle with polygons. And the idea is that if you put in enough sides for the polygon, they ought to turn into the circle. But no polygon is the same as a circle, but as you take the limit, as you put in more and more and more sides of the polygon here, they start to look more and more like the circle. So that concept has been around, like I said, for more than 2,000 years. The limit concept showing up for tangent lines and areas is more recent, but even there, what basically happened is people had a good intuitive understanding of it, but when they tried to write down a definition that was always working, that's basically 1820s with a guy named Cauchy. And so it's a concept that can be grasped intuitively. To work with it in terms of a mathematical definition took much more time. We're not going to get that deep into it, but we certainly want to have a good intuitive understanding of the limit concept. So here's the notation that's used. Of course, f of x is a function like we talked about last time. The x approaches c means that the values of x, the inputs, are going towards the point c. C is some fixed number. And then the L stands for the limit. So we want to know, what does it mean for the function f of x to have a limit value of L as x approaches c? So here's some words for it. Again, mathematicians like to use symbols to shorten things, but that can create problems. You definitely have to know what the symbols are. So the limit of f of x as x approaches c, that's what the arrow is going to be L. And this really is an equals sign here. I'll say more about that in a moment. So another way to think about it, if you go back to our arrows and targets, is we're saying that if the input values, the x values, the arrows, if they're close to the number c, this is a big deal I'll say more about in a moment, they're not equal to c. You don't choose that arrow, you choose all the ones that are close to it. You shoot them over to the target, those are the outputs, and they're all landing pretty close to L. Okay, so here's one of the problems that comes up with this. It's tempting to say, when you have this limit idea, to say that as x gets closer and closer to c, f of x gets closer and closer to L. And that's, again, a decent intuitive way, but it's actually not mathematically correct. I don't think I'll say more about that now. It's just, this really is a concept that is challenging to define carefully. So let's look at one example, and the first example is going to seem completely trivial, but there's more going on than meets the eye. So down here we're saying that for the function x cubed, so we're doing f of x is the function x cubed. Then we're saying that the value of c is 2, that's the specific number. And we're saying that if x is close to 2, x cubed is close to 8. Well, most people say, well, duh, 2 cubed is 8, why not? But again, that's not what this statement is saying. This is not saying when you plug in 2 you get 8. It's saying when you plug in numbers close to 2, 2.01, 2.003, 1.998, and so on, you're getting numbers very close to 8. Okay, so again, as x approaches the number 2, the outputs are approaching the number 8. So here's some other examples where things are not quite so easy. So for instance, for this first one, if you try putting in 2, you get 2 minus 2, which is 0, over 4 minus 4, which is 0. You get 0 over 0. And that is a meaningless ratio. It means absolutely nothing. Here as x approaches 1, remember we talked about the natural log of 1 is 0, so this is 0 over 0. 10 to the 0 is 1, so we get 1 minus 1 over 0. I'll say more about the second one, or the last one here in a moment. So the idea is this is why we don't care about what happens at C, because the function may not even be defined there. And even if it is defined there, it's irrelevant. We want to know what happens when the inputs are close to C but not equal to C. So for all these things, these 3 first examples here, we get this meaningless ratio 0 over 0, and we'll see when we start talking about derivatives, that's the kind of thing that always shows up, these 0 over 0s, and we need to figure out what's going on. When calculus was discovered, it was looking at all these ratios of 0 over 0, and what the heck does that mean? Well, one option for some of these is to use some algebra. So if we go to this first one, and we do some factoring, again, this is the algebra type of stuff that I'm talking about. You should know how to factor the difference of 2 squares. So x squared minus 4 is going to factor as x minus 2, x plus 2. And the reason for that is if you multiply it out, the middle term cancels. You get a positive 2x when you multiply these guys together, and then you get a negative 2x when you multiply those guys together, and they cancel. Then you're left with x squared and negative 4. So then we can do the cancellation. So we're still taking the limit as x approaches 2, so we have to recopy it. Then the x minus 2 terms cancel, and we're left with this. Now, it's important to realize that as functions, this function technically is different than this function, because the second one makes sense when you plug in 2. The first one doesn't make sense when you plug in 2, because you're back to this 0 over 0 stuff. But when we're taking the limit, we don't care what happens at 2. That's why we're allowed to cancel them. And now we know that as x approaches 2, we get 2 plus 2, so we're going to get 1 over 4. So for this first limit here, which started off in that 0 over 0 form, we could use some algebra and remove the problem and then come up with an answer. These other ones, this one and this one, we're going to have to wait until we learn some more stuff before we can do. I want to take some time to talk about this function. Again, let me go back. You're supposed to know or have seen some trig functions, so the graph of cosine is the one that looks like this, and then it goes on forever. This is pi over 2, this is pi, and so on. This is 1, this is negative 1. But we're doing things differently here. You're having this pi over x stuff. So as x gets close to 0 in here, 1 over x gets really big. It's like if you put in 1/2 for this guy. Now let's put in even a bigger number. Put in 1 over 100, something really close to 0. Well, that's the same as the cosine of 100 pi. That ends up being 1. And if you put in a different number that's really close to 0, let's go with 1001. That's cosine of, remember, invert and multiply, so we get 1001 pi's. Then if you remember how this sine or this cosine graph goes, it just keeps doing this. And so here you are at pi, you're at negative 1. At 2 pi, you're at positive 1, and then it just keeps repeating. And so anytime you have an even multiple of pi, 2 pi, 4 pi, 6 pi, you get 1. When you have the odd multiples, pi, 3 pi, and so on, you get negative 1. And so the idea is that no matter how close x is to 0, there's always values where you get an even multiple of pi and other values where you get an odd multiple. So the graph, it keeps bouncing back and forth between 1 and negative 1. If you try to sketch a graph of this with a computer or by hand, you can't do it because it ends up doing weird stuff like this, and then some graphs will try to give you this black screen here before they start doing this again. So this is a good example of a function that looks perfectly reasonable, cosine of this, but it's impossible to draw the complete graph. And as you go on in mathematics, you'll find that there are more and more situations like that where you cannot visualize it with a graph, but you can still understand it by playing around with various properties. So this is an example of a function where the limit does not exist. There is no number L such that when x is close to 0, the cosine of pi over x is close to L. So it is possible for limits not to exist. Okay, what do we have next here? This is an option that we can sometimes do, and if there's nothing else you can do, it's worth trying, and that is plug in numbers. So suppose we want to find the limit of this function, 1 plus 2x to the 1 over x power. Let's do a simple example. If you put in x equals 1/2, this would say 1 plus 2 times 1/2. That's 1 plus 1. And then you take 1 over x, and that's going to be 1 over 1/2, which is 2. So we get 2 squared, or 4. If you put in 1/3, you're going to get 1 plus 2/3. And then you're going to raise that to the 1 over 1/3, that's to the 3rd power. So we get 5/3, and that's cubed. That's going to be 125 over 27, which you can see is 4 and a little bit more. But these guys I'm just putting them in to show how this function works. They aren't close enough to 0 to help us find the limit, so then we bring out a calculator and we start plugging in small numbers on both sides of 0. So we plug in 1 over 100, negative 1 over 100, 1 over 1,000, negative 1 over 1,000, 10,000, and so on. And if you start looking at this and start looking for a pattern, and I tossed these numbers in just so maybe there's something weird that's going on with these ones and zeros. So let's try some other numbers. But you can see they're all giving us roughly the same thing. And so as you look at these last ones and look at the first few decimals, it appears that whatever this limit is, it's going to be somewhere near 7.389. Now let me go back, because up here with this one, we're back to this guy. It's true that when you plug in numbers close to 2 and cube them, you get numbers close to 8. So like if you put in 1.99995, cube that, you get something really close to 8. But we're saying that the limit is exactly equal to 8, because the closer the inputs are to 2, we're going to have outputs that are also within a smaller range of 8. So we really are putting equals. The reason I'm putting in squiggles here is because this is not the exact value of the limit, but it's a good approximation, so we know that this limit exists, but we don't know what its value is exactly. And again, a few weeks into the semester, we'll be able to prove that the limit is actually that number e squared. And we can prove that carefully. But for now, all we're saying is that we're getting a rough approximation. The limit does exist. We don't know the value, but we know it's close to 7.389. Again, that's a subtle distinction, but one that's important to be thinking about. Okay, so there are times when you use a calculator to come up with an approximation. The kinds that we're going to be working with are more like this type, where we can do some algebra to figure out what's going on. So in this particular case, recopy the limit because we haven't done anything yet. So if you just try the normal thing, put in 3, you get 9 plus 9 minus 18 in the top. In the bottom, when you plug in 3, you get 18 minus 15 minus 3. So you get back to that 0 over 0, which is not helpful. That tells us nothing. So we need to do something else. However, by plugging in 3 and getting 0 over 0, we know that x minus 3 has to be a factor in both the top and the bottom. So that's helpful. In the top, if you factor out an x minus 3, we have to have an x here, and we want to get negative 18, so that's going to be a plus 6. In the bottom, we want a 2x squared, so we're going to have a 2x here. We want to end up with a minus 3, so I guess we need a plus 1. And you can check this. If you multiply this out, there's the 2x squared, then you get minus 6x plus x, that's minus 5x, and then the minus 3. And then this is equal to, we can cancel out the terms. And as before, the reason we can do this is because we don't care what happens at 3. We want to know what happens when x is close to 3. And then now we know what's going on, because the numerator, if x is really close to 3, the numerator is really close to 9, the denominator is really close to 7, and so we get 9/7 for the value of the limit. Now do pay attention when you're doing these to the notation. The notation stays because in each of these cases we have not taken the limit yet. It's only in this last step that we actually took the limit. The reason I didn't do the cross out method up here by doing something like this is because if you cross it out too darkly, you can't even see what happened. And so that's why I kind of like putting in the extra step of just showing what happens after you do the cancellation. So again, do pay very careful attention to the notation. Okay, so that's the kind that we're going to be often looking at, but again, we have these two options. Do some algebra and hopefully figure out what's going on. Use a calculator and see if we can figure out at least what an approximate limit would be. Okay, limits have some properties. They're make pretty good intuitive sense. So right now we're supposing that the functions f and g do have limits at the point C, and then we're just letting k be some generic constant like 2 or pi or 47. So this is one of those things where to prove them carefully from the definition takes some effort. You certainly want them to be true because they make intuitive sense. At the level of calculus, we just want them to make sense. At the level of real analysis, which is a course here in the 400 level, that's where we prove all these things carefully, because if you're going to go on in mathematics, it is important to know how to prove them carefully from the definition. For us, right now, we just want them to make sense. So this is saying that if you want the limit of a constant times a function, you just find what the limit was and then multiply by the constant. So if you know back to what we did before, this was 8. It's not a surprise that if you take the limit as x approaches 2 of 3x cubed, you're just going to get 3 times 8. That's all that that's saying. So don't let the symbol scare you. This is saying that if you add two functions, the limit is just the sum of the two limits. If you subtract, then you subtract the limits. If you multiply, then you multiply the limits. And no surprise, if you divide the limits. Now if you think about it, we've already been using these properties, right? When we did this problem up here, we took the limit of the top and said, okay, we know that that's going to approach 9. We took the limit of the bottom and we said, well, we know that's going to approach 7. And so we're really using this property here. That's how we got the 9/7. So the idea being that even if you don't even think about these specific properties, you probably would end up using them anyway. So that's what we were doing up here. So that's why they should make intuitive sense. Okay, we'll talk about these properties and see them show up in other applications, but again, we're not going to be proving them, but you should certainly believe that they work. Okay, what else do we have here? Oh yeah, we need to look at one-sided limits because those are something that we'll need. So you can see the difference here is right there and right there. So before it was just x approaches c. And notice when we were doing the numerical stuff, we were putting in numbers that were both bigger than c and smaller than c, positive and negative in this case because we are approaching 0. we do want to know what happens on both sides. However, in some cases, we only care about what's happening on one side. And so that's where these things come into play. So we're on the number line. Here's the point C. C plus means C plus a little bit more. So you're talking about points out here, which, given the way we draw the number line, are on the right-hand side. So that's why it's called a right-hand limit, because you're plugging in numbers to the right of the point that you care about. They're a little bit bigger. And then down here, you're plugging in, for the left-hand limit, you're plugging in points on this side. So the only difference is, it's still the same short symbols, it's still the same words. The only difference is, for the right-hand limit, you're looking at input values that are close, but they're a little bit bigger, versus close, but a little bit smaller. So right hand, left hand, C with a plus, a little bit bigger, C with a minus, a little bit smaller. Then basically everything else is the same. You're just narrowing the number of points that you look at, one side or the other. So they're called one-side limits because you only care about what happens on one side of C. Then you go back, and the other one you call a two-sided limit. Typically, limits are by default two-sided unless something else is said. So we have one-sided limits, two-sided limits. It's probably, well, let's just make a quick observation. All of these properties hold for one-sided limits. So you could put C plus on all these and it would still work. Okay, so that's no big deal. Intuitively, that should make the same sense as it did before. And furthermore, this limit, the normal limit, the two-sided limit, has the value L if and only if the two one-sided limits both exist and they're equal. So I suppose maybe we should draw a quick picture. So here's an example where something goes wrong. If you have a function that does this, and then for some reason there's a break, and then it does this. This would be an example where the function has that for the left-hand limit, and then this for the right-hand limit. So as you approach C along these values, the f of x values are getting close to L. If you approach C from this side, you're along this part of the curve and you're getting close to the number R. But this doesn't have a two-sided limit because the L and the R values are different. So for a function to have a two-sided limit, a normal limit, both one-sided limits have to exist and agree. If they exist, but they're different, like in the picture, then we say the two-sided limit does not exist. Okay, so we've got all that stuff. Let's do an example. Remember, this is why you need to be paying attention to the previous lectures. What was this thing? That was our greatest integer function. So it represents the biggest integer that you can get that's less than or equal to x. So let's take a look at this. So for this first one, x is approaching 5, but it's a little bit bigger than 5. So you're putting in things like 5.2, 5.03, 5.001. And the greatest integer smaller than those guys is 5 for all of them. So you're going to get this. But if you come from the other side, 4.98, 4.997, and so on, those numbers are really close to 5, but they're smaller, and the greatest integer is just going to be 4. So in this particular case, the one-sided limits exist, but they're different. And then we could conclude that the limit as x approaches 5 of the greatest integer function does not exist. Again, if we drew the graph, we'd see something like that. Okay, let's do some other one-sided limits just to think about these things. And again, that's really is the point of this, is just think about what the symbols mean. So in this case, we're plugging in numbers that are close to 2, but smaller. So things, again, like 1.99 and so on. So notice that the top and the bottom are going to be, quote unquote, the same number. It's just that the bottom will always be positive and the top is going to be negative. So this ends up being -1. So again, if you want to see this, put in, let's just do 1.99 minus 2 over, then down here you put in the absolute value of 1.99 minus 2. When you do that in the numerator, you get negative 1 over 100. Down here, it's the same thing, but you took the absolute value. That's where we're getting -1. So again, the idea is that the numbers are the same except for a minus sign. That's why it's -1. Okay, let's take a look at this next one. It's got this guy in it. So now we're thinking, okay, we're putting in numbers close to 7, but a little bit bigger than 7. So if you think about that, as x approaches 7, x is going to approach 7. That's a no-brainer. Minus, now we're talking about the greatest integer. So you're putting in things like 7.1 and so on. The greatest integer there is also 7. So you get 0. But while we're at it, let's take a peek at what would have happened if we had come in the other way. So now instead of plugging in things like 7.1, we're going to be plugging in things like 6.9. Well, the x stuff is still going to get close to 7. As x approaches 7 from either side, x is getting close to 7. But now for numbers like 6.9, 6.99, and so on, the greatest integer is going to be 6. So it's approaching 6. So we get 1. So once again, we would conclude that the limit as x approaches 7 of this particular function, that does not exist, because the two one-sided limits are not equal. Okay, what else do we have in here? Here's another one. Now this, notice, is a two-sided limit, so I have to be a little bit careful. So let's see what happens if we put in two generic values, one on either side. We'll just try two random ones and then sort of generalize. So if you put in something like 5.1, you're going to get greatest integer less than or equal to that is going to be 5. Then if you put in the 5.1, you get negative 5.1. There's 5. There's negative 5. If you put in 5.1, you're sitting right there. So the greatest integer is going to be negative 6. Which of course gives us negative 1. If you put in something like 4.99, so let's see, this is where I was before. So if you put in something like 4.99, now you're sitting here, and negative 4.99, you're sitting here. So in that case, when you plug in those numbers, the greatest integer is going to be a 4 and then a -5, which is still -1. So it looks like on both sides we get the same number. Therefore, the two-sided limit exists and has the common value, -1. Okay, so these examples, they aren't difficult, but they certainly force you to think about what the limit means and what the greatest integer function is. Here's one more using the greatest integer. So again, you need to be careful. Not hard, you just need to be careful. So let's plug in a number close to -3, but a little bit bigger. Let's try -2.9 and see what would happen. Well, if you do this, then you're going to get the greatest integer of -2.9/2 minus the greatest integer of 2 times -2.9. What's that going to give us? Well, this is going to give us a -1.45. And then this is going to give us a -5.8. So with negative numbers, you have to be careful. You want the greatest integer that's to the left smaller than this number, so we have to go to -2. And for the other one, we want to be smaller than 5.8, so that means we need to go back to -6. So we're going to get 4. And again, you can try this if you use 2.998 or something. Same thing's going to happen. This is always going to be close to -1.5, so it's going to go back to -2. And this is going to be close to 6, but always a little bit smaller than -6. And so that's why you have to use this guy. Sorry, a little bit bigger than -6. So this guy ends up being 4. Okay, so these are all algebraic examples of doing this. I know some people, visual works better, so that's what this last example, it is the last example, is going to be. We're going to take a look at a graph. Now it's a rather bizarre graph, but again, functions can be of any type, and we're trying to learn how to figure out what goes on no matter what the function is. So here's the graph of our function, and when you see a graph like this, it's assumed that it just keeps going this way and going this way forever. When you see these bullets, that tells you what the value is at that one particular point. So if you plug in -4, you're going to get 1, and so on. Let's see if I can do this so I can still see the graph and answer these questions. So let's take a look at what happens at -4 first. So if you come from the left, -4 from the left, you get 1. If you plug in -4, you get 1. If you come at it from the other side, you're getting -1. Is everybody okay with that? Can we see this? So the next thing we care about is what happens at -1. So let's go up and see. At -1, if you approach from this side, you're going to get 2. Approach from this side, you're going to get 1. And the value of the function is 2. So we're going to get, we said this was going to be 2. The function was going to be 2. And this was 1. So again, as you approach -1 from the left-hand side, you're going along this part of the graph. That's why you get 2. If you're approaching here, you're going along this part of the graph, and so you're running towards the point 1. And if you actually plug in the number -1, you're up at the bullet point there, which is 2. So that's where we got the 2, 2, 1 for those answers here. Okay, so the next set has what happens at 1. So can we see what happens at 1? Well, f of 1, where the bullet is, that's 1. If you come at it from the left-hand side, we're down at -2, going along here. And if you come at it from this side, you're going along there, so that's going to give you 2. So in this case, all three of the numbers are different, the value of the function and each of the one-sided limits. Then the last set is what happens at 2. So you can see here, when you plug in 2, you get 2. The left-hand limit is 2. And the other one, oops, they're 3. Duh, 3. As you approach this way, you're going towards that point. So when you plug in 2, you get 3. The limit from the left is that, and then you get a 4. So these guys are going to be 3, 3, and 4. And just a couple of, well, let's do one trivial remark. What's f of -5? Well, you come down here at -5, you get 1. What's f of 4? I come to 4, and it's 4. But suppose someone said, what's f of 1/2? So again, this doesn't involve limits, but it involves things that we've done before. Now, of course, you could say, well, okay, 1/2, and come down here and you can make a guess, but the idea is that we don't want to guess, we want the exact value. Well, from the picture, it's clear that the function is a line that goes through the points -1, 1, -1, 1, and then it goes through 1, -2 as well. So then we could find the equation of the line that goes through those 2 points. Using the point slope form, we'd have y minus 1 is equal to -2 minus 1, so that's -3, over 1 minus -1, so that's 2. Then we're using the point on the left, so it's x plus 1. So that would be the equation of the line for that part of the curve. If you plug in x equals 1/2, we get y is going to equal -3/2 times 3/2 plus 1. That's -9/4 plus 4/4, that's -5/4. So this thing is that value. So I think that should do it for today. Again, this last stuff is just practice with the graphs and also a review about linear equations. So that's why it is important to keep up with everything, and again, continue to ask questions if there are things that you don't understand.